Module 2, Section 2.1, Functions. Objectives. Objective 1. Use point-by-point plotting to sketch the graph of an equation in two variables. Objective 2. Understand the definition of a function. Objective 3. Use vertical line test to identify a function. Objective 4. Evaluate a function and identify the graph of a function. And Objective 5. Use the graph of a function to determine the values of x or y. Objective 1. Sketch the graph of an equation using point-by-point plotting. The graph of an equation in two variables is the set of all points whose coordinates satisfy the equation. One method of graphing such equations is the point-by-point plotting method. Find several ordered pairs that are solutions of the equation. To find ordered pairs, substitute numbers for x and find the corresponding values for y. Plot these ordered pairs as points in the rectangular coordinate system. And finally, connect the points with a smooth curve. Here is an example. Graph y equal to x square plus 2. Make a table of ordered pairs that satisfy the equation. Here we have calculated a set of ordered pairs. If x equal to 3, I can calculate the y value as 3 square plus 2, which is equal to 11. Next, plot the points and connect them with a smooth curve. You may need to plot additional points to see the pattern formed. This is how the graph will look like. Example, sketch the graph of y equal to 9 minus x square. Make up a table as follows. Choose integer values for x to calculate y. So for example, if you need to calculate y value corresponding to x equal to negative 4, substitute in the formula like this: 9 minus negative 4 square, and that will be equal to 9 minus negative 4 square will be positive 16, and that will be 9 minus 16, which will be negative 7. That's how you get this negative 7 here. Now we need to plot all these points. X equal to negative 4, y equal to negative 7 will be plotted as a point up here. The next point will be negative 3, 0. X is negative 3, y is 0, so that will be on the x-axis, second point. Negative 2, 5. So x is negative 2, y value is 5, so that will be the next point. Then continue like that. X equal to 1, y equal to 8, that will be this one. Now what we need to do is we need to join these points by a smooth curve. And this is how the graph will look like. Here we are going to use the graphing calculator to show the graph of y equal to 3x square. So we go to the function editor, which is written as y equal to, and then type in the formula 3x square, 3x to the power 2. Now if we get the graph, we will get this shape. These are some of the graphs of basic functions. Here we have the identity function. We have the squaring function here. This is called the cubing function. We have the absolute value function, square root function, and the last graph will be that of the cube root function, x to the power 1 by 3. Objective 2, function. A relation is any set of ordered pairs. Domain is the first coordinates or the x values in all of the ordered pairs of the relation. Range is the second coordinates or y values in all of the ordered pairs of the relation. For example, if the relation is given as this set of 4 ordered pairs, 5, 7, 10, 11, 9, 8, and 12, 14, then we can write the domain as all the first coordinates or the x value. So this will be going in the domain, 10 will be in the domain, 9 will be in the domain, and this 12 will be in the domain. So the domain is a set of x values 5, 10, 9, 12. And the range is the set of y values or the second coordinates. If we collect them all, we will get 7, 11, 8, and 14. So write it as a set. We will get the range of the relation. Notice that we cannot repeat members in a set. Function definition. You can visualize a function by the following diagram, which shows a correspondence between two sets. D is the domain of the function that gives the diameter of pizzas, and R, the range of the function, gives the cost of the pizza. So for example, this arrow which is going from 16 to 12 means that the cost of a 16-inch pizza is $12. And we will interpret all the ordered pairs like that. A function is a relation for which every x value in the domain has one and only one y value. That is, not two different ordered pairs have the same first coordinate. So here are two examples, one of which is a function and the other one is not a function. If I write this in the ordered pair form, I can write the first diagram written as the set of all ordered pairs 1, D. Then there is an arrow going from 2 to C, so that will be the ordered pair 2C. And there is another arrow going from 3 to C, so that will be ordered pair 3C. And this satisfies the criteria for a function that every x value in the domain has one and only one y value. So if you collect the domain points, this will be the first coordinates 1, 2, 3. So that is a set up here. And the range will be the set of second coordinates, that will be D, C. Notice that C is repeated twice, but in the set we are only listing it once. These arrows can be translated as the relation containing the ordered pairs 1D, 2B, and 2C. So the domain of this relation is going to be the set 1, 2, and the range is the set second coordinates, that will be D, B, C. In a function, this kind of arrows are not allowed. So that is what we need to notice here. Example, determine whether each relation is a function. We are given this relation consisting of 4 ordered pairs. And we notice that this is a function since each x value has a unique y value. If we convert this in the arrow form, we have 3, 5, 4, 6, and 3 goes to 9, 5 goes to 16, 4 goes to 12, and 6 goes to 20. And here is another example, again with 4 ordered pairs. We need to check whether this relation is a function. And notice that in this case we have 7 going to 8 because of this ordered pair here. And if you look at the last ordered pair, 7 is also related to 4. So that means we will have an arrow going from 7 to 4. And this is not allowed in a function. So the second relation is not a function. In this example, we need to indicate whether the table specifies a function. Notice that 14 has 2 y values. 14 is going to 14 through this arrow, and 14 is also assigned to 10. That is not allowed in a function. So this table does not represent a function. Objective 3, vertical line test for a function. If you have the graph of an equation, there is an easy way to determine if it is the graph of a function. It is called the vertical line test, which states that An equation specifies a function if each vertical line in the coordinate system passes through at most one point on the graph of the equation. If any vertical line passes through two or more points on the graph of an equation, then the equation does not specify a function. Here are two examples. The first graph is not the graph of a function because you can draw a vertical line which crosses it twice. So this is not a function. Vertical line test more than one point. The second graph is the graph of a function because any vertical line crosses only once. So wherever you draw the vertical line, it crosses the graph only once. If that property is there, it is the graph of a function. In this example, we need to indicate whether the graph specifies a function using vertical line test. So if you draw any vertical line, in the first graph there can only be one intersection, so this will be a function graph. In the second graph, we have a vertical line where it crosses the graph more than once. Here it is intersecting at 2 points. So vertical line test fails here, so we can say that this is not the graph of a function. Objective 4, function notation. If the name of a function is f and the variable is x, the function can be represented by the function notation f of x. Use the function notation to rewrite the following functions using the given function name. So we are given y equal to 7x minus 4 and the function name is f. Then we can write the function using the function notation f of x equal to 7x minus 4. So if we are given y equal to 5t square plus 4 and if the function name is g, then we can write the function using function notation as g of t equal to 5t square plus 4. Notice the variable here is t. Function notation is useful because the variable whose values make up the domain is easily identified as the variable inside the parenthesis. Function evaluation. To evaluate a function at a certain value, substitute that value for the variable in the expression and simplify. Suppose we consider the function fx equal to 6x plus 3. Find the value of the function when x equal to 3. In symbols, we say we want to find f of 3. And what is f of 3? F of 3 is obtained by substituting the value for x as 3. So we will get 6 multiplied with x value is now 3, then plus 3. 6 times 3 plus 3. That is what 6x plus 3 means. So when we do this one, we will get 18 plus 3 equal to 21. To find a function's value when x is some number a, we write f of a. The point is shown on a graph by the coordinates a, f of a. Consider the function f of x equal to x square plus 2. What does f of negative 3 mean? We need to replace x with the value negative 3 and evaluate the expression f of negative 3 equals negative 3 square plus 2 equal to 11. So which means that the point negative 3, 11 is on the graph of the function. Here are some more examples. F of x equal to square root of 3x minus 2. And we calculate f of 2, which will be replacing x with the 2. So we get square root of 3 times 2 minus 2. That will be square root of 4 equal to 2. If we replace x with a, we can write f of a as square root of 3 times a minus 2. Find the domain of the function f of x equal to 7x to the power 6 plus 5x to the power 4. For any real number x, we can calculate 7x to the power 6 plus 5x to the power 4. So that means any real number can be in the domain of the function f of x. So the answer to this question will be domain equals all real numbers. And we sometimes write this as an interval notation, and the interval is open interval negative infinity, infinity. In the second example, we need to find the domain of the function f of x equal to square root of 3x minus 2. We know that we can get a real number only if we calculate the square root of a non-negative number. Otherwise, it will be a complex number. So we need to insist that the square root is calculated on a non-negative number, which means 3x minus 2 is greater than or equal to 0. This is a kind of condition on x. If we add a 2, we will get 3x greater than or equal to 2. So that tells me that if I divide with positive 3, I will get x greater than or equal to 2 over 3. So the domain in the second example will be all real numbers that is greater than or equal to 2 by 3, or also written as the interval 2 by 3 to infinity. In this example, we are going to use the given graph of a function f to determine the y value to the nearest integer. If we are given y equal to f of 2, what is the y value nearest to the integer? So what this means is x equal to 2, and we need to calculate y from the graph. So this will be x. So if x is equal to 2, we are going to look at here and then go to the graph and read the y value horizontally from the y-axis here. So y value equal to 5, which is going to be the function value corresponding to 2. So I can answer this question as f of 2 equal to 5. Also find x when y equal to 3. So that means I need to calculate x here with a given y value 3. So this time what we need to do is we need to start with the y value, which is 3, go to the graph and then read the x value from the x-axis. So this x value will be 1. X equal to 1 when y equal to 3. An application. If r of x is the revenue function and c of x is the cost function, then the profit function is defined as p of x equal to r of x minus e of x. And we have an example here where the revenue is given as 85x minus 3x square and the cost is given as 135 plus 15x. So we need to calculate the profit function p of x and determine its domain. Let's do the calculation here. P of x equal to r of x minus e of x. Now if I replace r of x, I will get 85x minus 3x square. That will be this r of x. Then subtract c of x, and c of x contains 2 times, so I need to use a parenthesis around. 135 plus 15x. When we simplify this, we will get 85x minus 3x square. Then notice that this negative sign is common for terms within the parenthesis, so we need to distribute that. So negative 135, negative 15x. And when we simplify this, we will get 70x minus 3x square minus 135. So this will be the profit function p of x. The domain of the profit function is the common domain of the revenue function and the cost function, which is 1 less than or equal to x less than or equal to 20. So we can answer the last part of the question. The domain of p of x is